Manasa madam, please start.
Good morning to all. I, Manasa KJ, Assistant Professor, on behalf of Department of Mathematics, Vidyavardhaka College of Engineering, Mysuru, welcome you all for today's webinar on the more Penrose inverse singular value decompositions and their applications. First of all, I would like to thank our HOD, Dr. N. Bhaskar, and Principal, Dr. Sadashiva Gowda, for giving the opportunity to organize this webinar. I welcome them for this webinar. Let me briefly introduce today's speaker, Dr. K. Manjunatha Prasad, Professor, Department of Data Science, MAHE, Manipal. He did his PhD from Indian Statistical Institution, Calcutta in 1993. Then he did postdoctoral research from 1994 to 1997 at ISI, Delhi. His area of research interests are generalized inverse of matrices and their applications, linear models, covariance matrices and applications, non-negative matrices, graphs and matrices in graph theory, network theory and applications. He has published over 50 journal papers in reputed journals, 3 edited volumes, 5 contributed articles, and 6 technical reports. He has completed 4 projects of national importance funded by SERB DST as well as Board of successfully guided 7 students for their doctoral program, and currently there are 5 students pursuing PhD under his guidance. He is in the editorial board of several journals, name a few: AKC International Journal of Graphs and Combinatorics, International Journal of Fuzzy Mathematics Archives, Research and Review Journal of Statistics, STM Journal, Annals of Operation Research, Special Matrices. He is also a member of American Mathematical Society, International Linear Algebra Society, Society for Industrial and Applied Mathematics, International Biometrics Society. He has served as referee for several international journals such as Linear Algebra and its Applications, Linear and Multilinear Algebra, Indian Journal of Pure and Applied Mathematics, and list goes on. He has around 26 years of teaching experience. Currently, he is associated with Department of Data Science, Prasanna School of Public Health, MAHE, Manipal, as a professor of mathematics. It is our pleasure to have such an eminent personality as today's speaker. On behalf of Department of Mathematics, VVC, Mysuru, I welcome you, sir. Over to you, sir.
Thank you, Dr. Manasa. This is my first experience to address a larger audience through online. Don't know how successful I am. Hopefully that I can communicate you as good as I am in front of you. Let us see what would happen. And also I am using this open board tool for making presentation, and it's again my first experience for using that particular board. I don't know how well I can write on this particular pad and communicate you. And also, first of all, let me thank the organizers, Department of Mathematics, Vidyavardhaka College of Engineering, for inviting me to deliver this webinar. Probably I am having 2 hours with me, isn't it? Hello? Am I audible?
Yes, sir, you're audible.
Yeah, you're audible.
I have 2 hours time with me, isn't it?
Yes, sir.
Yes, sir. Last 10 minutes, we'll keep it for question and answering, sir.
Yeah, then let me try to finish it as early as possible. Yeah, contents of my talks are in this line. First of all, let me spare some time with the preliminaries, and I'll introduce the notion of generalized inverses, and then later move on to eigenvalues and eigenvectors. This is well known to you, most of you. I don't have to go through the basic too much, but still I'll put up some effort in describing the same thing in my own way. Then later I'll describe singular values and singular value decomposition, and I'll touch upon some applications in the field of engineering. Okay. These are the notations that I use. This R is for set of all real numbers. This is for complex numbers, and R m by n for set of all m by n matrices for real numbers. This Rn for n-dimensional vector spaces. That is set of all real column vectors of order n. And for a matrix, need not be a square matrix of size m by n. This notation A to the power t stands for transpose of A, and this C of A stands for column space of A, and this particular R of A for column space of A transpose or row space of A. And I write rank of A in this way. And then later, let me move on to next page. Yes. Let me start with the preliminaries. Okay. These are two simple things. I don't, most of the things I don't repeat. So m by n matrix means it consists of m into n real numbers or complex numbers arranged in m rows and n columns. And when I write or say a matrix is diagonal, then on the diagonal you may have non-zero entries and rest of the entries are 0. And In denotes identity matrix of size n by n. Okay, these are all two simple things that I don't, but I can always talk about this inverse, because I'll continue from here to describe generalized inverse of a matrix. If A is a square matrix and if there exists a B such that A into B, B into A, that is equal to identity. And such in a matrix is denoted by A to the power -1, or we call it inverse of A. And of course, other notations not really required. I use it elsewhere. So I'll skip and I'll move on to generalized inverse. So the moment you talk about generalized inverse as the term inverse appears, and along with that the word generalized is also there. So as I mentioned earlier, if I have if A is a square matrix and if its rank is full, then you have a matrix B such that A into B is identity matrix. Similarly, B into A is identity. So it is denoted by A to the power -1. Now, if given matrix A is m by n matrix, not a square matrix, okay? In such a case, I look for a candidate which plays the role of A to the power -1. So why do we look into these matrices? The moment we talk about linear algebra, we talk about solving a linear system, isn't it? Ax is equal to b. If I have a linear system of this kind, I like to find x so that Ax is equal to b. In case matrix is square and inverse exists, then I can have that Oh, that's what happens. Okay, you multiply by A inverse, so you get, or you get x is equal to b. That means x, I missed A inverse here. See, so blackboard is not really, it cannot be replaced by something else. Anyway, we are to get acquainted. A inverse b happen to be a solution. So such that A into A inverse b is this b. So when you have a system Ax is equal to b, that is consistent. I mean, it has a solution if b can be written as linear combination of columns of A. Hope that I am making it understandable for you. So it has a solution or consistent if this B happen to be linear combination of columns of A, or I say B belongs to column space of A. Okay. Sometime we like to achieve this B in a practical situation, and I have a model matrix A, and I look for suitable input X such that I'll be able to achieve B. Now, we may set several targets in our life. We may not be able to achieve it, isn't it? So in such a case, what do? If I cannot achieve it, then at least try to reach that goal as near as possible, isn't it? So usually matrix A is treated as, if it is of size m by n, then it is treated as mapping from this is Rn, this is Rm, and this happen to be a mapping from Rn to Rm, and the range or column space of A need not be entire this Rm. It may have only part of it. Okay, the range of A may cover only part of this Rm. That means sometime what I want to achieve may be lying somewhere here, outside this particular range. So in such a case, I still look for suitable input through this particular model to achieve this B. So when I cannot reach this B, then what I do, within the possibility, that means within this range, I try to reach a point as close as possible with this particular point B. So I look for X here, so that my A, if I say that as X naught, somewhere here, so that the distance between what I like to achieve, that B, and this AX naught is very close. Sometimes you may come across a different situation. Given system AX is equal to B, B may be achievable, but we may be able to achieve through several X's. That means solution is not unique. In such a case, I come across, there will be a question in front of me, which solution to be chosen. So I like to, whenever I can get something at the cost of say 50 rupees and somewhere else at 60 rupees, what I'm going to do? So I'll buy the same item at 50 rupees with the minimum cost. So like that, here we look for X that takes me to B in most economical manner. So that means here we use the norm of vector as weight or value of or the expenditure that I am going to have. So one with the minimum expense, that means one with the minimum norm, a solution with the minimum norm that I like to have in some occasions, even when the AX is going to be is achievable. Okay. So these are the few things that we come across when we deal with solving a linear system. Okay. Now, in this context, I define generalized inverse. If I have A, I multiply by A inverse to get identity, and again multiply by A, I get A, isn't it? So whenever inverse exists, I have A into A inverse into A, that is equal to A. So keeping this in our mind, we define this generalized inverse. Here, A need not be a square matrix. A could be any m by n matrix. If there exists a matrix of size n by m, so that multiplication is going to be compatible, such that AGA is equal to A, then G is called generalized inverse. Okay. So this is also known as one inverse because of a particular reason, which I'll come across. There will be a set of equations called Moore-Penrose equation. This particular condition happened to be the first among them. That's why we call it one inverse, or we call it pseudo inverse. Instead of calling it a generalized inverse, we may call that as pseudo inverse. Initially, it was also called partial inverse in the literature. Okay, and we use this particular notation. Forgetting this one in the A inverse, we keep only this minus sign. A minus is a notation for generalized inverse. And let us see whether we have unique generalized inverse or more number. In fact, there are more than one, and set of all generalized inverse is denoted by this class of A minus. Now, consider, I'm with AX that is equal to B, a linear system. If I have G such that AGA is equal to A, then what happens? Suppose this B is in the column space of A. That means AX is equal to B is consistent. In such a case, let us see what happens to this GB. Okay. So that is equal to, now look into this GB. Okay, B is in the column space of A, and the above is consistent. So we get that is equal to AGA X that is equal to AX that is equal to B. What does that mean? This GB is a solution. So if you have a generalized inverse, you can propose a solution that GB happen to be a. Suppose you have GB is a solution for every consistent linear system. Okay, then we can prove easily that G is a matrix satisfying this AGA is equal to A or generalized inverse. Okay. Now, if AGA is equal to A, then multiply by G, what do you get? You have AGA is equal to A, multiply by G. So what do you mean by that? That means this AG is idempotent. Okay. Similarly, GA happen to be an idempotent matrix. And when you talk about idempotent, what do you mean by that? That happens to be a projector. I'm carefully using this particular word. The moment you hear the word projector, you may get confused with the orthogonal projector. So it is not orthogonal projector, it is just a projector. So a matrix is called a projector if E square is equal to E. Okay. So its null space need not be orthogonal to the range of A. So if it is orthogonal to range of A, range of E, then it is called orthogonal projector. Okay. So here AG and G are orthogonal. Are idempotent. So in such a case, you just look into matrix GA is idempotent. Consider I minus GA. Okay, you take any a vector of this kind, then you get A into this, that is equal to A minus AGA into X, and AJ is A, so that is 0, isn't it? So you take any vector of this kind that happen to be in the null space of A. Okay, A of that vector is that. In fact, set of all vectors in the null space of A is given in this form, I minus GA into X for some X. So if you have linear system of AX is equal to B and GB is a solution, as I mentioned earlier, if G exists, then this plus I minus GAZ Z arbitrary gives you set of all solutions for AX is equal to B. So if A is invertible, what happens? When A is invertible, GA happen to be G happen to be A inverse. So I minus J is 0. So this becomes 0. You have unique solution. Otherwise, I minus GA happen to be non-zero. In such a case, you have plenty of solutions, maybe infinitely many solutions for AX is equal to B. So sometime if AX is equal to B, then we look for a solution with the minimum norm, okay, or the solution that one with the minimum cost. Okay. And if matrix G is a generalized inverse of A, then what about its uniqueness? If A is invertible, then generalized inverse cannot be more than one. Only one generalized inverse, that is the inverse. Otherwise, there could be, as we find infinitely many solution for Ax is equal to B, there are infinitely many generalized inverses. That is given by is running somewhere. Yeah, it is given by G plus I minus GA into U plus V into I minus AG. Look into these matrices very carefully. By pre-multiplying A here, you get A into I minus GA is 0. Okay. Similarly, by post multiplying by A here, you get this particular part. When you multiply, you get 0 matrix. So that so that I get A into this given matrix A into this matrix into A happen to be A. So these are all happen to be different generalized inverses of A. Does it exist? That is the question in front of you. If exists, I have given you the class of generalized inverses. Of course, it exists. In the first point, I am taking rank factorization of matrix A. In the second example, second case, I am taking this particular kind of decomposition. Okay, when I take rank factorization, that is B is a full column rank matrix and C is full row rank matrix. This is of size M by R. This is of size R by M. So B is left invertible and C is right invertible. In such a case, I consider this CR the left inverse of this C and right inverse of this C and left inverse of this B and multiply and get a new matrix G, and it can be verified that such G is a generalized inverse of A. Okay? Or if I take this kind of decomposition for given matrix, okay, so in that case, if this is of size M by N, I take a block matrix of size N by M, the corresponding block, okay, block correspond to this IR, I keep IR, then in the rest of this 0 block, these 0 blocks are not of same size, depending on the size of this matrix M by N. So the size of these vary. So correspond to these blocks. Okay, I take arbitrary matrices and pre-multiply by inverse of this Q and post-multiply by inverse of this P and get a new matrix G. And one can play with this matrix and verify that G happen to be a generalized inverse of this A. Okay, I don't like to bore you too much with these notations. Again, instead of taking IR, if I have some invertible block here, I can get generalized inverse easily in this manner. And reflexive generalized inverse, the word reflexive appears here. Okay. So G is a generalized inverse of A, and if that A happen to be generalized inverse of G, then we call it reflexive generalized inverse of A. Now, I already described you earlier. We may have the case where this is a range of column space of given matrix A, and here is the A happen to be mapping between Rn to Rm, where the range is not complete Rm, okay, and you have some part of this Rn, the domain, is null space of the notation I use is, okay, null space of A. That means the elements from this null space of A goes to 0. So in such a case, I have several solutions for Ax is equal to B. Okay. Okay. Here I have several choices in Rn which goes to this particular B. My B is here. My B is here. So all the vector from here goes to this B. Okay. So among these, which one is best for me? So I look for X. Among X, this norm of X is minimum. Among all, Ax is equal to B. So in this case, I look for a candidate among generalized inverses, which provide this particular solution. Okay. So in that context, we define minimum norm generalized inverse. Okay. So a generalized inverse G of A is said to be a minimum norm generalized inverse if in addition AGA is equal to A, it satisfies GA transpose is equal to GA. Look into this condition carefully. This condition GA transpose is equal to GA. GA is idempotent, I told you earlier. Taken GA multiplied by GA again, I get GA again, GA. So GA is an idempotent. Here I have GA transpose is equal to GA. That means it is symmetric or Hermitian. Okay, it is Hermitian and it is a idempotent. That's why it is orthogonal projector. Okay, GA is orthogonal projector. So if G is a generalized inverse which gives a orthogonal projector, then it happened to be a minimum norm generalized inverse. In other words, okay, for any y belongs to column space of A, that means Ax is equal to y, this particular linear system is consistent. Okay, for any y belongs to column space of A, X is equal to G satisfying this property. Okay, this property is a solution of Ax is going to be with the minimum norm. Okay, so this Gy provide a solution with the minimum norm. So if I look for a solution with minimum norm for the given system Ax is going to be, then I find a minimum norm generalized inverse and use that one to get minimum norm solution. Similarly, as I mentioned earlier, my target is beyond the range. This is my B. Okay, I have a linear system. Ax is equal to B. Okay, this is the mapping that gives you this one, and I like to achieve this, but not possible because of my model matrix. This A. Okay, A is given because of the practical situation constraints. Okay, I'm with this design matrix, and I like to achieve this B. I know that is not possible. In such a case, as I told you earlier, through some X here, go to a place here which is nearest, okay, to this B, nearest to this B, and for this particular point, say B naught, which is very close to this B, there may be several candidates. My first objective is to find at least one that takes me to very close to this B. Okay. Once I have such candidate and I find there are several more that will take me to this particular nearest point. Then among this choice, I like to have one with the minimum norm. Okay. Now, first of all, let me look into the first case that gives me an element here that takes me to the closest one. What do you call such solution? We call such solution as least square solution for this Ax is equal to B. Okay. So here we have the definition of least square generalized inverse. A generalized inverse, or we call it G inverse, G of A is said to be a least square G inverse if, in addition to AGA is equal to A, it satisfies AG transpose is equal to AG. Here, again, as I explained earlier, oh, no, not this. Okay, this AG is an idempotent, AG transpose is equal to AG, that means it is symmetric and idempotent. That's why this AG happened to be an orthogonal projector. Okay, orthogonal projector onto range space of A, in fact. Okay, so it is orthogonal projector. So a generalized inverse which gives you AG an orthogonal projector onto range of A, then it is called least square generalized inverse or least square G inverse. Okay, so we can verify that G is satisfying this property AGA is equal to A and AG transpose is equal to AG if and only if for any xy, okay, the norm AGY minus y is less than or equal to norm AX minus y. Okay, x is arbitrary. When x is arbitrary, then what happens to this AX, set of all AX, that gives you the range of A. So x is such that, okay, not x, this GY is a solution such that AGY minus y, okay, this GY is an option among x. Okay, so such AGY minus y is less than or equal to norm AX minus y. Okay, that means among all AX available here, okay, Here I have written B instead of Y. You'll have to excuse me for that. So this norm Ax minus Y means the distance between these. Okay. So AGX, am I with this? Yes, no. Okay, the GY is here. Among all AX here, this AGY minus Y, take its norm, here it's B, AGB minus B is less than or equal to norm AX minus Y, the distance between all any AX and this B. Okay. So matrix G satisfies this property if and only if that GY provide a least square solution for AX is equal to Y. Here Y need not be in the range of A, or AX is equal to Y need not be consistent. And I have talked about the other solution. The GY gives one choice here when G satisfies that least square generalized inverse, that G is a least square generalized inverse. Now there are several, plenty of choice that takes me to this particular point, nearest point. So I wanted one having the minimum norm. For that, who is the candidate? The candidate for that is a matrix satisfying these four conditions. The first one is AGA is equal to A, GAG is equal to G, and AG transpose is equal to AG. AG is symmetric idempotent, and GA is also symmetric idempotent. So this is called Moore-Penrose inverse. So on this occasion, I must tell you that exactly 20 years back, great statistician C.R. Rao born in 1920, and even this same Moore-Penrose inverse was invented in the same year. So we have spent 100 years after the invention of this particular notion. In fact, unfortunately, it is not going to happen in this year. We wanted to have ICLA International Conference on Linear Algebra and its application. So we wanted to dedicate a day in the honor of C.R. Rao, as well as celebrating the invention of this Moore-Penrose inverse. Okay, the very invention, the notations were somewhat cumbersome and not so easy to understand. Then later, independently Moore invented a matrix satisfying these four conditions, and also observed that it satisfies all the requirement. Okay. So now we are writing a matrix satisfying this AGA is equal to A as A minus. Remember, now as time progressed, for this minus sign, another perpendicular line was kept. In fact, it's plus sign. Okay, so we denote this matrix G satisfying these four conditions, okay, by this and called Moore-Penrose inverse. Okay, in fact, one can play with these conditions and verify that such generalized inverse exists and unique. Okay, so such Moore-Penrose inverse provide a given linear system AX is equal to B. It gives a solution among these with the minimum norm. Okay. This is a game to be played with this A plus and verify that it is unique. And no, this is for construction of rank factor Moore-Penrose inverse. If you have a rank factorization B into C, then B transpose B, that happen to be a positive definite matrix and full rank matrix, and you can find inverse, and you can have B plus given by this notation and C plus by this notation, this expression C transpose into C transpose inverse. So I'm not going to verify and bore you people. And this exists, and A plus Moore-Penrose inverse of A is given by this C plus. Here A is B into C plus into B plus happen to be A plus, satisfying all those 4 conditions. Okay, that has been verified here. I'm not going to repeat and spare precious time. And here is a again computation that verifies if there are 2 Moore-Penrose inverse, that is to be unique. Also, if you go check that carefully, no, I don't like to bring in that particular notion. Now, I like to tell you how to construct this Moore-Penrose inverse. That is very much important when it comes to application. Okay, suppose A is of rank 1. Okay, life is very simple in that case. A Moore-Penrose inverse is given by the transpose into some scalar. Okay, if A is given, you can find its a transpose very easily. What about this alpha? This alpha is nothing but simply trace of A transpose A. So here is a rank 1 matrix. You can simply play with just to break the monotonicity. You can verify A is a matrix of rank 1 because the second row is twice the first row. So it is of rank 1. So you can construct Moore-Penrose inverse easily. First of all, you will have to find A transpose A, check that it happens to be this matrix, okay, so that you can get engaged along with me. So multiply, take A transpose and multiply with this A and see that A transpose A is given by this matrix. So once you have that, you can find this alpha, that is trace. Just take the diagonal 25 and 45, add it, you get trace of this trace of A transpose A is this 70. Okay, you get A transpose is equal to 1 by alpha into A transpose. Okay. But don't play the same trick when rank is not equal to 1. Okay. So it is not so simple. That is where the singular value decomposition comes for our help. Okay. So this I don't discuss it now. Unfortunately, I kept this particular theorem over here. I'll come back to this slide once I discuss the singular value decomposition. Okay. So before that, let me play with this notion of eigenvalue and eigenvector. All of you have dealt with this notion of eigenvalue and eigenvector when you were in BSc or BTech first year. Okay. So given n by n matrix, this eigenvalue and eigenvectors deals with only square matrices. So if A is a square matrix, say it is of size n by n, say it is over real numbers. Okay, consider characteristic polynomial of that. How do you get the characteristic polynomial? And it is of degree n. That is given by A minus lambda I. This A is a square matrix. Lambda is a variable. Okay, take A minus lambda I. So you have a square matrix again and take the determinant of this. Okay, that gives you a polynomial in this lambda, isn't it? On the diagonal of this matrix, you have lambda term. Okay, in fact, aii minus lambda you have. Okay, that is involved in the determinant. You get polynomial of degree n. So say that b of lambda is equal to determinant of a minus lambda I. Okay, then equate that one to 0. That means you equate this determinant of a minus lambda I is equal to 0. Equivalently, you have this lambda so that a minus lambda I is singular. That means not non-singular. That means not invertible. Okay. In other words, a minus lambda I has non-zero null space. Okay. So you find such lambda. That lambda happen to be the eigenvalue. The roots of characteristic equation. When you equate that one to 0, you call it characteristic equation. Okay. Characteristic equation of a square matrix A is called eigenvalues, or we call it characteristic values of A. In other words, lambda is said to be an eigenvalue of A if there exists a vector x not equal to 0. Okay, A of 0 is always 0. It is trivially an eigenvector. Okay, so that is not something that we look at. So we take non-zero vector x such that Ax is equal to lambda x. Okay, we call x is an eigenvector correspond to this particular eigenvalue lambda. So that's all about eigenvalues and eigenvectors. Again, to break the monotonicity, you can take rough sheet and check. For this A is equal to 0, 1, 3, 2, a square matrix of size 2 by 2, you take A minus lambda I. So that happens to be minus lambda 1, 3, 2 minus lambda. Okay, take the determinant and equate that one to 0. You get characteristic equation given by minus lambda into 2 minus lambda minus 3 is equal to 0. So if you simplify and find the roots, you get lambda is equal to minus 1 and 3. There are two eigenvalues, okay, for this particular matrix. So eigenvalues are minus 1 and minus 3. Again, you can take the matrix A minus lambda I for these values of lambda minus 1 and 3 separately and find its null space to find the eigenvector correspond to these minus 1 and 3 respectively. Okay, so this is how you can find eigenvalues and eigenvectors. Eigenvalues need not be distinct all the time. Here, fortunately, we had that to be different. It need not be same. The number of times an eigenvalue lambda occurs as root of the characteristic equation is called algebraic multiplicity of lambda. Okay. Look at this particular case. Okay. Here for this matrix, okay, minus 1, 0, 1, lambda, 5, 1, 1, 0, 1. Okay, with this you have characteristic equation can be factorized into lambda square into 5 minus lambda. Therefore, 0 happen to be the root with the multiplicity 2. Okay, and 5 happens to be root with the multiplicity just 1. Okay, just because you have 0 as eigen value, I don't say that the rank of this matrix is 1. Okay, don't get confused with the number of non-zero eigenvalue and rank of this particular matrix. Okay. Okay. Then if lambda 1, lambda 2, lambda n are eigenvalues of n by n matrix, square matrix, then we can factor characteristic polynomial as follows. Determinant of this a minus lambda I given by lambda I into lambda, product of lambda I minus lambda, and then by setting lambda is equal to 0, we observe that determinant of A is the product of eigen values. When I put lambda is equal to 0, what happens? That A minus lambda I happen to be simply A. So the product of eigen values happen to be determinant of A. Then again, you can check that coefficient of lambda to the power n minus 1. Again, for that, you will have to appreciate determinant expansion of this one and observe that this coefficient of this lambda to the power n minus 1 is given by trace of the matrix. So that happen to be simply sum of all eigenvalues. Okay. Now let me bring in, I'll have to keep track of time, otherwise I may not be able to go to application. Oh, I already spent 1 hour time. Okay, I'm within my time limit. So I'll have to introduce this orthogonal matrix. A square matrix P is said to be orthogonal if P transpose happen to be its inverse. That means P into P transpose is identity matrix. Similarly, the P transpose P is identity. Okay. Here, we will have to observe one thing. If A is a symmetric matrix of size n by n, then you can observe that there exists an eigenvector, okay, correspond to real eigenvalue. Okay, here without going into depth, I am assuming sorry, it created several blank pages. Okay, where am I now? Yes. If A is a symmetric matrix, then let me reveal a truth for non-mathematicians that A has real eigenvalues. You see, depending on lambda I minus, depending on of nature of this particular polynomial, it may have real root or may not have real root, isn't it? Sometimes we may end up with having complex roots only, okay? But in case you are with a real and symmetric matrix, then you are assured of having real eigenvalue. you are assured of real eigenvalue. Then you will be having an eigenvector. Okay. In such a case, take unit eigenvector. Once you have eigenvector, you can have a unit eigenvector easily by multiplying by the inverse of its norm. Okay, you have unit eigenvector correspond to that eigenvalue alpha, and B is equal to alpha times V transpose is a matrix satisfying the following properties. Okay, that B is a matrix of rank 1 such that AB is equal to BA is equal to B square, and rank A is equal to rank B plus rank C, where C is equal to A minus B. Okay, I don't want to go through the traditional proof of spectral decomposition. So it is in fact something which you may not find it in any standard textbook. Okay, this particular result you may not be finding in any standard textbook. It uses some tools of minus partial order, which I don't like to discuss now. Without mentioning the minus partial order, I am describing this particular situation. So given a symmetric matrix, you can always find B, okay, of this type, alpha times V transpose, where V is eigenvector correspond to this alpha, satisfying these properties. A into B is equal to B into A is equal to B square. In other words, B into A minus B or A minus B into this B is 0. What do you mean by that? What do you mean by that? B into A minus B is equal to 0, and here A minus B into B, that is equal to 0. What do I mean by that? Here A is symmetric matrix, B is also symmetric matrix, B transpose. See, remember. Okay, so B transpose is equal to 0 means the rows of this B, okay, rows of this B are orthogonal to columns of this A minus B, but B and A minus B are symmetric. That means the column space of B and A minus B are orthogonal to each other. Similarly, rows of A minus B and this one, columns of this B are orthogonal to each other. Okay. So given symmetric matrix, you can have such matrix B. Okay, you can write B is equal to A is equal to B plus C, where C is equal to A minus B, and rank of B is equal to rank of B plus rank of C is equal to rank of A. Let us look into the proof very quickly. This B is eigenvector. I told you earlier it exists. Okay, you can't say that for this symmetric matrix there is no real eigenvector. There exists a real eigenvector, and AV is equal to alpha times V. Okay, then you construct this B, and because this V is eigenvector of this A, you can verify easily that AB is equal to BA is equal to B square. It requires little patience. You can just make substitution and verify that AB is equal to BA is equal to B square easily. Now B is eigenvector. Therefore, range of B or column space of B is subset of range of A, because alpha is there in the column space of A. Therefore, range of C is also in the range of C. Okay. Now you see that range of B and range of C are orthogonal. That's what we checked. Okay. BC into CB is equal to 0. Okay. They are orthogonal to each other. Therefore, range of B direct sum range of C is range of A. Therefore, rank of A is equal to rank of B plus rank of C. So this B satisfies these two properties. So what is the advantage? The advantage is from here on I can prove spectral decomposition theorem easily. Okay, as I told you earlier, I am giving you completely different proof for spectral decomposition. So how is it? Start with A. Now I don't go through those slides straight away. Let me have this A. Okay, and construct. If A is of rank 1, okay, then A is of this form. This B is itself A. Okay. So these are unit vectors. So you have vector V, column vector V, row vector V transpose. Okay. So that you get B is equal to this alpha. Alpha happen to be eigen value. You can check very easily. So that is B into alpha into V transpose. You extend the basis. You get orthonormal basis extending this V. So you get matrices, orthogonal matrices P, and B is equal to that P into this alpha. And on the diagonal you have alpha and rest are 0 into this P transpose. Okay, if rank is 1, you are with the spectral decomposition theorem. Otherwise, use this particular lemma. You construct B satisfying this property. Now, when you construct this B is such that B into C is 0 and CB is equal to 0. B is symmetric, therefore C is also symmetric, and rank of this C is 1 lesser to rank of A. So you follow the method of induction. So by induction you have spectral decomposition for this C. Okay. Now you have B is alpha times VV transpose. Now use the decomposition for C and adjust them together to have decomposition for this A. Okay. A is n by n symmetric matrix. Then there exists orthogonal matrix P such that P transpose AP is this diagonal these things, or A is equal to P into diagonal matrix into P transpose. So as I mentioned earlier, it's by this thing induction. Okay. So if A is of rank 1, then as I mentioned earlier, it is easily observed. Otherwise, you construct B and C as I mentioned earlier, and you get C is in the form of V into diagonal lambda 2 lambda R and this one V transpose. Okay. And then later you have this A by adjusting this V with the U1. Okay. So you get spectral decomposition for this A. Now it is necessary to have a symmetric matrix to apply spectral decomposition. So if you have A here, you can get spectral decomposition easily in this manner. So what you do is construct, just look into A minus lambda I and find the eigenvalues, eigenvectors. Okay, eigenvectors you find here. Eigenvalues are 3 and 1. Once you have these eigenvalues, you find corresponding eigenvectors, and with the help of eigenvectors, you have this. Okay, you have eigenvectors, unit eigenvectors. Here you have eigenvector -1 and 1. Unit eigenvector is simply obtained by multiplying by 1 by multiplying by 1 by norm of this, that is the square root of 2. So correspond to this particular eigen value 1, we have eigenvector minus 1 by root 2, 1 by root 2, and for this 3, the other one, okay, 1 by root 2, 1 by root 2. So use that to obtain P and P transpose. In the middle, you have eigenvalues of this A, where A is symmetric matrix here. Okay, so this is how we obtain spectral decomposition. Okay, when matrix is symmetric and square, then you have spectral decomposition. Otherwise, what to do? That is where we look for a different notion called singular values. So before that, let us look into a matrix which is symmetric. If it satisfies this particular condition, x transpose Ax is greater than or equal to 0 for all x, then we call it positive semi-definite. If it is strictly greater than 0, we call it positive definite. So it is necessary to have symmetric matrix. In addition to that, these properties to call it either positive definite or positive semi-definite. Okay. Now you consider any matrix A. There is a typo here. Okay. Let this be m by n matrix. This should have been m by n, not n by n. Okay. Now you take A transpose or A transpose A. Okay. A transpose A that happen to be of the form something is happening. Control set is not coming. And anyway, let me manage. Next time I'll get expertise on this matter. Okay, here you take A transpose A. A is in a rectangular matrix, so you take X and X transpose arbitrary. Okay, now what is this one? This is inner product of AX with AX, isn't it? So that is equal to 0 if and only if AX is equal to 0. Otherwise, that happen to be norm of AX and it is always greater than or equal to 0. Okay, it is always a positive semi-definite. Whenever it is positive semi-definite, let us take the help of spectral decomposition and find square root of that. Take spectral decomposition of A transpose, okay, or A transpose A, whatever it may be. And on the diagonal, what do you have? Eigenvalues of A transpose. Okay, there are all non-zero diagonal entries are strictly positive. Okay, so then you can take square root, retain same P matrices. Okay, so you get square root of that A transpose. So whatever the square root you have, okay, that happen to be eigenvalues of A transpose to the power half. Okay, these non-singular, these singular values. Okay, these singular values are non-negative because we take non-negative square root. Okay, and you can arrange them this way, this manner. Sigma 1 of A, that is singular value. This happen to be maximum. Sigma 2 is 1 next to that, and sigma n, this could be 0. Okay, kept in decreasing order, and singular values can be kept in this particular order. Okay. Here is an example for square root of A transpose. Let me save some time. Okay, it is already 11:45. A lot of our application as fast as possible. Again, just similar to the earlier case, I can present some independent proof for singular value decomposition. Since I already described in the case of spectral decomposition theorem, I don't have to go through each and every step in this case. But I can describe you to make believe. For M by N matrix A, there exist orthogonal matrices U and V such that A is U and diagonal sigma 1, sigma 2, sigma r and rest are zeros into V transpose. Okay, this need not be a square matrix. Okay, this is a rectangular matrix. Even rectangular matrix which is not square, we can discuss diagonal entries. Okay. So on the diagonal you have these entries, rest are zeros, where sigma 1, sigma 2, sigma r are singular values of A. Okay. So this is possible. You can take just A transpose and take their eigenvalues and take spectral decomposition for A transpose and play this and continue. Okay. And find eigenvectors for this A transpose correspond to all those singular values, correspond to these singular values, and then later you can find the vector, not vector, other P also in the similar way, okay, and obtain this matrix V transpose, okay, so that A is U into this D000, this is diagonal matrix with the singular values on the diagonal into this V transpose. Just to get the feeling of this, I'll take the simplest case where A is this matrix A of rank 1. Okay, so A transpose happen to be this 9 minus 9 minus 9 9, and eigenvalues are 0 and 18, and the singular value happen to be square root of this eigenvalue of A transpose that happen to be square root of 18. Here it is going to be 1 by 1 matrix. Okay, so U1 is this. The corresponding eigenvector you will have to find that happen to be minus 1 by root 2, 1 by root 2. It's transpose because the eigenvector, that's always column vector. So you extend the orthonormal basis and get this. Okay. Similarly, you get V in this particular form. Okay. And your A is given by this U D00, where D is this 1 by 1 matrix that is given by square root of 18. Okay. Okay, this is all about singular value decomposition. Am I going very fast? Anyway, let us look into some application in the field of engineering. I'll go through just 4 or 5 small examples. Okay, just to say that, convince you that there are some applications. Maybe some of the engineers sitting among you may be better expert to discuss on the applications of this eigenvalues, singular value decomposition, and Moore Penrose inverse. Okay. Let me consider the case of eigenvalue first. Okay. And take an example from mechanical engineering. Now, consider any material it is stretched or compressed through a linear operation. Okay, I'm not going to twist it. Okay, I'm interested in taking this linear operation. Okay, I stretch it or compress it. Then the direction of maximum deformation is called principal direction. Okay, people may be interested in having this principal direction for the application purpose. Okay, this example is taken by this particular book by Kenneth Cutler. The title of the book is Linear Algebra Theory and Applications. Okay, suppose that deformation is given by this matrix A. Okay, if you know each coordinate, how it is stretched, then you can find this particular matrix A. Okay? If you have that matrix, that happened to be square matrix. Now in 3 dimension you will be stretching, and you have this particular transformation. Find its eigenvalues. If that A happened to be this matrix, then eigenvalues are given by 0, half, and 3. And find corresponding eigenvectors. Okay, among the eigenvalues, is 3 is the maximum. Okay, 3 is maximum. Corresponding eigenvector, you can verify and see that it is 3 by square root of 11, 1 by square root of 11, and 1 by square root of 11. This is a unit vector. So principal direction is given by this particular vector. Okay. So this is how you can see the one among the importance of eigenvalue and eigenvector. Then let us, okay, I promised something else to you earlier and missed it. That is very much important. I should not miss that. Why should I find this singular value decomposition? Okay, that helps me in finding Moore-Penrose inverse. Okay, what is the advantage of Moore-Penrose inverse? That gives me the minimum norm least square solution. Okay, when I cannot achieve the target B through the matrix A, if Ax is equal to B and B is to be determined, okay, and it is not within the range of A, then I look for minimum norm least square solution. Okay, so to find that I require Moore-Penrose inverse. Okay. For that I require Moore-Penrose inverse. How do I make use of this singular value decomposition? Consider A is equal to P into, this is the diagonal matrix, okay, with the singular value sigma 1, sigma 2, sigma r, where r is the rank, and the rest are 0 entries into Q, a orthogonal matrix. Okay. In that case, earlier over there I might have written V and U transpose or something. Okay. Here I have written P and Q. Okay. The Moore-Penrose inverse is given by, here sigma is diagonal matrix, non-zero entries, so I can find its inverse easily. Just take inverse of those diagonal entries to find sigma inverse. Okay. U transpose multiplied by sigma inverse x, y, z, p transpose. That gives me any generalized inverse, and instead of any x, y, z, let me take 0, 0, 0, I get Moore-Penrose inverse. Okay. So more Penrose inverse of A is given by a matrix of this kind with X, Y, Z as 0 blocks. Okay? So that's how I can make use of singular value decomposition. Okay. Here in the image processing, we have an interesting application of singular value decomposition. Okay. Suppose you have image. So it is a grayscale image that can always be represented by a matrix depending on intensity of each pixel. Okay. Each entry of the matrix describes the intensity of corresponding pixel. Current digital files uses integer numbers between 0 and 255. It may not be same even now, I don't know. Okay, depending on intensity, you find some, keep some number. Suppose that A is a grayscale image of size 1000 by 1000. Okay, so what is the size of the matrix? It is 1000 square entries are to be there. It is too large to make any entry. So you want to capture this image, want to send it to, if it is a satellite image, you want to send it to the laboratory at Earth, isn't it? Then sending so many, that is 1 million numbers, okay? Difficult. So this is where we are going to make use of singular value decomposition. Now consider singular value decomposition of this A. What is A? A represents your image, the intensity of each pixel. Okay, that's what it gives. Now consider singular value decomposition of that particular A. Then, in case, say, A is of rank 1, hypothetical case, okay, then you don't have any of this. In such a case, what are you supposed to transmit? Only the entries of U1 and entries of this V1 and this S11, isn't it? That is enough. You don't have to transmit all the numbers. Of course, the nature of A is also going to be simple when A is of rank 1. So we may not be having such trivial cases all the time. Okay. So singular value decomposition is of this form. This K could be anything lesser than this N, depending on the rank of A. Okay. Now, what satellite does? So we know the limitation of the satellite. It cannot send all those data entries properly. Then what we look for is just look at in this U matrix and V matrix. Find 20 columns here, and here you look for 20 rows. There is no obligation on this number, depending on your ability. Consider some finite number lesser than the rank. Here rank could be any bigger. It need not be 20. It could be even more than that. If rank is lesser than 20, then again you can confine to the same number. Suppose rank is 10. It is enough if you send the entries in the first 10 columns here and first 10 rows of this and 10 entries of this S. Okay. Otherwise, what you do? You take some number, say 20, less than the rank of A, and send those numbers. Okay, 20 numbers, 20 enters in the 20 columns. That means 20 into 1000. Similarly, 20 into 1000 from here, and 20 enters here. Okay, that is 40,020. Okay, you transmit only this much of information. Okay, you can transmit these numbers, this many numbers, instead of transmitting all the 1 million number. Okay, then what happens? You may not get exact picture what you receive. You will get blur image. Okay, but you may be satisfied with that blur image depending on your requirement. Okay, so what do you get? You get first 20 components of entire spectral decomposition. That means you will have to add some more positive semi-definite matrices here to get exact A. Okay, but because of our limitation, we will be satisfied with whatever the blur image we obtain with this information. So, unfortunately, I did not give appropriate reference. It is not my own. It is stolen information. I should have acknowledged here just below, which I didn't do it. Sorry for that. Anyway, I have reference towards the end to inform you. Okay. If you take just one singular value, you get this kind of image. You take 5 singular values, you get this image, and rank of that matrix happen to be 499 in a particular example. Okay, if you take all 499 singular values, the image will be of this type. When you compromise with the transmission, okay, number of entries, then you have different kind of image. Okay, so depending on your ability and requirement, you can set your transmission properly so that you get image properly. Okay, here is an example from electrical network. Suppose that we have an n-port network N with the impedance matrix Z. Okay, impedance matrix Z. Then V is equal to Z into I. Okay. Suppose we want to produce a particular output V naught. In that case, we want to solve V naught is equal to Zi. This is something to do with input, correct? Okay, V naught is equal to Z into I. If V naught is not in the column space of Z, it may not be a full rank matrix. Okay, some matrix Z. Suppose it is not in the column space, then we will have to look for approximate solution. Remember, earlier I talked about least square minimum norm solution. Okay, so that will be given by Moore-Penrose inverse. Okay, this would be okay. Which solution we want when it is not consistent? Okay, when there is no solution, I look for a solution, particular solution that is given by Z plus V naught. V naught is something that we wanted. Then later we find Z plus, that is Moore-Penrose inverse of Z. Z plus V naught is the output which is very close to this V naught under the Euclidean norm. Okay, so that's how we can make use of Moore-Penrose inverse to find the best input that we can provide to reach as close to this required output V naught. Okay, here I have one more application of Moore-Penrose inverse. Okay, that is applied for removal of blur in an image caused by uniform linear motion. Again, this linear motion is important. Okay. The following idea is discussed in this article: application of Moore-Penrose inverse of matrix in image deep blurring. Okay. Now let G be R by M matrix corresponding to degraded image. Okay, this corresponds to degraded image. Suppose that L is the integer which indicates the length of linear motion blur in pixel, and let F belongs to R by N real matrix, okay, corresponding to original image where N is equal to M plus L minus 1. Okay. Then G transpose is equal to H1 F transpose, okay, and G is F H1 transpose. In fact, should have been H2, where H1 is a matrix corresponding to the, okay, oh sorry, I thought we have written other way. It is G is equal to F H1 transpose only, transpose of this. Okay. Where H1 is the matrix corresponding to horizontal degradation phenomenon. Similarly, matrix form of the process of vertical blurring of the image is given by G2 equal to H2F. Here, H2 and H1 we can determine. Here, ultimately, G is the one that we have. Now, we are interested in obtaining this F. Okay. Here, G is actually what we obtain after this degradation along columns as well as rows is HC F HR transpose. This is what we have, G. Now we are interested in looking for the original, but it is not so easy. Okay, if HC is left invertible and HR is right invertible, then we can get this F very easily. But it may not be the case all the time. So in such a case, we look for the best possible solution. Okay. How do we get the best possible solution? We take the help of Moore-Penrose inverse. Moore-Penrose inverse of this HC and HR. Okay. So I'm not going to describe these things, and I'll give you the solution that is given by the F. We cannot achieve, but one close to that can be achieved by using Moore-Penrose inverse of this HC into this G. G is the one what we have, the blur image, into this HR. Okay, yeah, Moore-Penrose inverse of HR transpose. Okay, so here we get best possible image, very close to the original one. Yes. So these are the applications that I wanted to mention. Just to convince you that yes, here are the application of Moore-Penrose inverse, singular value decomposition, and eigenvalues and eigenvectors. Of course, you can refer to these references. The first one is very useful to understand on generalized inverses and minimum non-solution, least square solution, and so on. The second one is very good for finding applications of linear algebra, and you have these two books, okay, sorry, articles. This is on so the third one is on matrices and digital images, and the fourth one is the article which consists of application of Moore-Penrose inverse in image deep blurring. Okay, yes, it is 12:10. Probably since I am not just there in front of you. I've gone a little faster than what I could. Usually, I expect people to interrupt me in between and get the clarification, so that usually whatever the material I prepared, that is going to be much more than that time allotted to me here. Opposite to that, I finished it much early. Probably I have done some cheating without giving sufficient justice. You'll have to pardon me. We can utilize another 15-20 minutes for any further discussion. How to go to
Thank you, sir. It is a wonderful session.
wait, let me get out of this. You want this slides for any reason?
Yes, sir. Yes, sir. Many are asking. Yeah.
Okay. Where is it?
At least the last one reference, sir.
Oh, this one. Yeah.
It is really wonderful to hear you again, sir. And any participants, if you have got any questions, you can post it in the chat box. Till now, I did not see any of the questions. Let me wait for another 1 or 2 minutes so that you can post your question. So I would like to ask one question.
Yeah, please.
Yeah. You mentioned that to find out the more Penrose inverse, that is one method is the rank, using the rank factorization.
That is one way of. Yes.
Is there any other method to find the more Penrose
Oh,
inverse?
there are plenty of methods. Even there are iterative methods. You see, whenever you have very large matrices, you cannot find a rank factorization and keep doing. The rank factorization, what we used is just to get convince ourselves how to construct. But in practical situation, there are several other methods, iterative methods, that is much more better for your computation purpose. Okay, if you refer to the work of Ben Israel, there is in fact, whenever we refer to generalized inverses, there are two interesting books, one by Rao and Mitra, the other one is by Adi Greville and Adi Ben Israel. So Adi Ben Israel, he discussed several iterative methods. In fact, he had several research articles also, in which he had given iterative methods, which is useful. Okay, whatever the methods I have given here, just for getting convinced to say that Moore Penrose inverse always exists. Okay, theoretically we can verify it.
Okay, sir. Thank you, sir. And one more person also asked the same question: how to find more Penrose inverse? You already answered it. Let us wait for another 1 or 2 minutes.
Okay, the purpose of the way I presented to raise some curiosity on generalized inverses and its applications. I don't know whether I could transmit my knowledge, very limited knowledge on this topic to you, but if it raises some curiosity and if it makes you to look into some literature related to this, I feel that the purpose is served. Okay,
yes,
please.
Sure. One more question is there, sir. Can we find the Moore Penrose inverse in C-star algebra?
In which algebra?
C-star algebra.
C-star algebra, it depends on involution what you have. Okay. If I'm correct, long back in '93, I did something in C-star algebra. I have some necessary and sufficient, given some necessary and sufficient condition, which I cannot recall. There are some interesting investigation related to this Moore Penrose inverse in fact, generalized inverses in this C-star algebra.
Okay, sir. No more further questions here. So now I welcome Mallige, Assistant Professor, Department of Mathematics, to formally give the vote of thanks.
Okay.
A very good afternoon to everyone present. I, Maliga Rajiv, deem it a great honor and privilege to propose the vote of thanks for today's talk. On behalf of VVCE and the Department of Mathematics, I would like to thank our resource person, Dr. K. Manjunatha Prasad, for his valuable time and effort in walking us through today's topic. I would also like to thank our management and our Honorable Principal Dr. B. Sadashivegowda for giving us the opportunity to organize this webinar. I also thank our HOD, Dr. N. Bhaskar, for his support and encouragement. I also thank all the participants for attending this webinar. The feedback link has been posted in the chat box and Telegram group. Thank you all.